Hello, and welcome to this SRC Learning Essentials series video about active standby pseudowire in H-VPLS. If you are not familiar with the Service Routing Certification Program, you can learn more by visiting our website at www.networks.nokia.com/src. In the following presentation, we will first describe pseudowire redundancy in a VPLS and explain how active and standby pseudowires can be used to provide redundant access to a full mesh network while avoiding loops. In our lab, we will then configure and verify active and standby pseudowires for a dual-homed multi-dwelling unit. Okay, so when a new MDU is added to a fully meshed VPLS, and the MDU supports IP-MPLS, the VPLS is extended to the MDU, allowing each customer to be connected directly to their own VPLS. This, however, would require the configuration of N-1 LSPs and N-1 SDPs on the MDU, where N equals the total number of PE and MDU nodes. In addition, the service provider must configure one LSP and one SDP towards the new MDU from every other participating PE and MDU in the network. This represents a large number of network touches and will occur whenever a new MDU is added to the network. Hierarchical VPLS reduces the full mesh requirement by using a mixture of mesh and spoke SDPs. This diagram illustrates that adding a new site in a hierarchical VPLS environment requires some configuration on the local PE router, but does not require any signaling of the other PE routers or MDU devices. In this instance, spoke SDPs are only required between PE4 and the new MDU. This significantly reduces the number of network touches required and simplifies the provisioning process. In addition, packet replication is reduced on the MDU and the bandwidth is used more efficiently. Alright, so let's add resiliency by connecting the MDU to two different PE routers using two spoke SDPs. Unfortunately, this setup introduces potential forwarding loops. In the diagram, broadcast, unicast, or multicast traffic arriving on the MDU is flooded on both spoke SDPs. Traffic arriving on the spoke SDP on PE1 is then forwarded on the mesh SDPs towards routers PE2, PE3, and PE4. Traffic arriving on the mesh SDP on router PE2 is then forwarded back to the MDU through the spoke SDP. The same applies to traffic arriving at PE2. As you can see, this creates a forwarding loop in the access network. For more details about SDP flooding behaviors, you can refer to the SRC Learning Essentials series video about spoken SDPs. So the question is, how can we provide resiliency and remove the forwarding loop without the need to run additional protocols such as RSTP? One option is to use active standby pseudowire. On this MDU, one of the spoke SDPs associated with the service is selected as active and will transport traffic, whereas the other spoke SDP will be in standby state. As indicated in the diagram, broadcast, unicast, or multicast traffic arriving on the MDU is forwarded only on the active spoke SDP towards PE1. Traffic arriving on the spoke SDP on router PE1 is then forwarded on the mesh SDPs towards routers PE2, PE3, and PE4. Traffic arriving on the mesh SDP on router PE2 is, however, no longer forwarded back to the MDU because PE2 is notified that this spoke SDP is standby. Thus, resiliency is achieved and the forwarding loop is removed. Let's now discuss how active standby pseudowire is implemented. On the MDU, an endpoint is created within the service and is associated with up to 4 different spoke STPs. Only one of the spoke STPs within the endpoint will be selected as active and will transport traffic, whereas the other spoke STPs will be in the standby state. In this example, the endpoint core is associated with 2 spoke STPs and the spoke towards PE1 is selected as active. Traffic arriving on the SAP associated with VPLS1 on the MDU is forwarded on the active spoke STP towards PE1, but not on the standby spoke STP towards PE2. In addition, transmit, receive, and learning are disabled on the standby pseudowire, and TLDP is used to signal pseudowire status between the MDU and PE routers. In this manner, the PE routers learn the spoke state and can take appropriate actions when the active spoke STP fails and a new spoke STP becomes active. So, to allow active standby pseudowire switching, each spoke STP is assigned a precedence value between 0 and 4. The default value is 4, and the lower precedence values are preferred. To clearly identify the preferred primary spoke STP, it is possible to assign a precedence value of primary. This is the same as configuring a precedence value of 0. From all spoke STPs associated with the same endpoint, the router selects only one as active. The selection is first based on the health status of the pseudowire, which is based on the pseudowire status reported from the local SAP and remote peering routers. If the health status is tied, the pseudowire with the lowest numerical precedence value is selected. And in the case of another tie, the one with the lowest SDP ID is selected. Various options can be configured on the endpoint. The revert time specifies the time to wait in seconds before reverting back to the primary spoke SDP after having failed over to a backup spoke SDP. Suppress standby signaling. When enabled, the standby pseudowire does not signal the pseudowire state to its pair. Note, if the network typically carries unicast traffic, it is usually better to tell the remote peer that the pseudowire is inactive by configuring no suppressed standby signaling. Next, we will move to our lab environment to complete this case study. There, PE routers 1 to 4 are fully meshed within the VPLS 30. We need to connect an MDU device to VPLS 30 using active standby pseudowire as a resilient loop-free path to the network. Alright, let's start the lab for active standby pseudowire. The first step is to create spoke STPs from PE1 and PE2 towards the MDU. On PE1, show service SDP shows we have an SDP ID of 5 with a far end address of 10.10.10.5, which is the system address of the MDU. So configure service VPLS 30 and spoke SDP 5:1 create. Over to PE2, show service SDP shows we also have an SDP ID of 5 with the far end of 10.10.10.5. So configure service VPLS 30 and spoke 5:1 create again. Now over to the MDU and run show service SDP, which shows us that the SDPs to the PE routers already exist. So let's configure VPLS 30. Configure service VPLS 30 customer 1 create, and create the endpoint, and we'll call it Metro create. Then no suppress standby signaling to allow the signaling of the standby pseudowire status. Exit. Next, we must create the 2 spoke STPs and add them to the endpoint. to PE1, spoke SDP 1:1, endpoint, metro create, back to PE2, spoke SDP 2:1, endpoint, metro create. And we'll set this spoke SDP as active by running precedence primary, back, and enable the service no shutdown. Before we test the active standby pseudowire, let's verify that the endpoint is operational by running show service ID 30 endpoint. Here we can see that both spoke SDPs are up. Also notice the precedence values. Spoke SDP 1:1 is set to the default of 4. However, on spoke SDP 2:1, we configured the precedence to primary, so its value is set to 0. So in this case, spoke SDP 2:1 to PE2 will be the active. Over on the PE routers, we can verify the pseudowire status by running show service ID 30 SDP 5 detail pipe match capital P lowercase w. And checking the pseudowire bits signaled by the pair, PE1 knows that this SDP is standby, while over on PE2, show service ID 30 SDP 5 detail pipe match PW shows its spoke SDP as not in standby state. Okay, before we test this setup, let's create a management interface on the MDU. This is an interface in a VPLS that is used to terminate management traffic, but here we can use it to verify IP reachability. Interface, let's call it test, create, address 192.168.30.6/24, just like in the diagram above. So you are aware there is already a management interface created on PE1 and PE2. Back over to PE2 to run ping router VPLS management 192.168.30.6 count 1. We get a successful response, and IP reachability is now verified from PE2 to the MDU. Running the same on PE1, also gives a successful response. Let's take a look at the FDB. Show service ID 30 FDB detail. This confirms that PE1 learns the MAC addresses through PE2 and not over the standby spoke SDP. On the MDU, show service ID 30 FDB detail also shows that we learn the MAC addresses from the active spoke SDP 2:1. As a final test, let's run a rapid ping to the MDU, and while it is running, shut down the active spoke SDP. On PE2, ping router VPLS management 192.168.30.6 rapid count 5,000. Over to the MDU, configure service VPLS 30 spoke SDP 2:1 shutdown, and show service ID 30 endpoint. This shows that spoke SDP 2:1 is now down, and spoke SDP 1:1 is up and the new active. Checking back on PE2, we see the new active spoke SDP is allowing the traffic to continue. And that's it for this video on active standby Pseudowire. Thanks for watching and see you next time. Content for this video was adapted from the Nokia Virtual Private LAN Services course. You can access the complete course via any of the 3 learning formats shown on this page, as well as get remote private access to a service router lab to complete the course lab exercises. If you are interested in obtaining an SRC certification, this table identifies the recommended courses and required exams for each of the 5 available certifications in the program.